This recording will look at the cardiac cycle and blood pressure. What we call blood pressure is actually the measure of the blood pressure, of the pressure of the blood in the aorta. The aorta is an elastic vessel, meaning that it's going to expand and recoil as the volume of blood pumped into the aorta by the left ventricle increases and decreases or decreases. So, the aorta, being an elastic blood vessel, is going to respond to changes in pressure by expansion and contraction. So, it's going to accommodate more blood when the left ventricle contracts and pumps blood out, and it will recoil when the pressure decreases. The pressure in the aorta fluctuates between 120 millimeters of mercury to about 80 millimeters of mercury. And this fluctuation corresponds to ventricular systole, ventricular contraction, when blood will be pumped out of the left ventricle into the aorta with high force, and the ventricular diastole, when the ventricle is relaxed, is not contracting, and therefore the pressure in the aorta decreases. So, blood pressure is a measure of aortic blood pressure. What moves blood through the body is blood pressure, meaning the pumping of the left ventricle into the aorta. That is the force that's going to push blood from the aorta to every other part of the body. MAP, MAP, stands for mean arterial blood pressure and is slightly less than the average of the diastolic and systolic blood pressure in the aorta. The reason why it's not the average is because we have to take into consideration that during the cardiac cycle, the diastolic phase lasts a lot longer than the systolic phase. So the low blood pressure number, the diastolic number, should weigh slightly more than the systolic number. But what we have to remember is the meaning of MAP, mean arterial blood pressure, and what MAP means. MAP is a measure of the blood flow reaching tissues. So the higher the mean arterial blood pressure, the more blood is reaching the tissues. The lower the mean arterial blood pressure, the less blood is reaching the tissues. So MAP is a measure of how well tissues are irrigated. MAP is dependent on two parameters: CO, which stands for cardiac output, and PR, which stands for peripheral resistance. We're not going to talk about peripheral resistance right now because that is dependent on the size of the blood vessels. And in this chapter, we're concentrating on the heart. We are going to talk about cardiac output, which is a parameter given by the heart itself. Cardiac output is it depends on the heart rate times the stroke volume. The heart rate is the number of times that the heart beats per minute. The average heart rate is 72 beats per minute. The stroke volume we talked about in previous PowerPoints is the volume of blood that's pumped out of the heart, and it is dependent on the end diastolic volume, and the end diastolic volume was the amount of the volume of blood in the ventricles when they are completely filled, after atrial systole, so this is EDV, the volume of blood inside the ventricles after atrial systole, minus the end systolic volume, which is the volume of blood that is left in the ventricles after the ventricles have contracted and pumped blood out. So the blood that's left in the ventricles is ESV, which means that the stroke volume, the blood that was pumped out, is the total volume, EDV, minus what's left after pumping. The average stroke volume is 70 mils per beat. So if cardiac output is dependent on heart rate times the stroke volume, the average cardiac output will be 72 beats per minute, which is the average heart rate, times 70 mils per beat, which is the average stroke volume. Notice that beats in the numerator of heart rate and the denominator of stroke volume are going to cancel each other, and the multiplication of these two parameters will be 5,400 mils per minute, which is the cardiac output. So cardiac output is the volume of blood put out per minute by the heart. If you convert mils to liters, we're talking about 5.4 liters per minute. So the average cardiac output is between 5 and 6 liters per minute. Now, because stroke volume is equal to EDV minus ESV, the volume, EDV, that fills the ventricle will affect the stroke volume, and so will the volume that's left after the ventricle has contracted. If we substitute the parameters that cardiac output represent in the MAP equation, now we're going to have heart rate times stroke volume times peripheral resistance as equal to MAP, to the mean arterial pressure. So notice that heart rate is directly proportional to MAP. If heart rate increases, so does MAP. Stroke volume is directly proportional to MAP. If stroke volume increases, so will MAP. Okay. So you should know what is cardiac output and how is it dependent on heart rate and stroke volume. You should know what MAP is, cardiac output times peripheral resistance, and how does heart rate and stroke volume can affect MAP. So again, MAP is cardiac output times peripheral resistance. Notice that MAP and cardiac output are again directly proportional, which means that if the cardiac output increases, so does the mean arterial pressure. So anything that increases cardiac output will increase the mean arterial pressure. So because cardiac output equals heart rate times stroke volume, again, these parameters will affect MAP. An increase or a decrease in heart rate will increase or decrease MAP and cardiac output. So heart rate, how many times the heartbeats per minute, will have an effect on cardiac output and on the mean arterial pressure. So you should know this equation and the parameters that affect the values, cardiac output and mean arterial pressure, and how does heart rate affect each of these. And we're talking about the relationship, the proportionality between them. If one goes up, the other one goes up. If one goes down, the other one also goes down. So you should know what is MAP and the relationship between MAP and cardiac output. You should know what is cardiac output and what is the relationship between cardiac output and heart rate. You should know the relationship between stroke volume, end diastolic volume, and end systolic volume. And what is the relationship between cardiac output and stroke volume. Again, if a stroke volume increases, so does cardiac output. This is what we call direct relationships. Okay, so the relationship between cardiac output and stroke volume, the relationship between stroke volume, end diastolic volume, and end systolic volume. So let's talk a little bit about these so that we can understand better how these parameters affect cardiac output. So we said that stroke volume equals EDV minus ESV. Okay, what happens if the end diastolic volume increases and the end systolic volume decreases? That will result in an increase in stroke volume because now we have more blood filling the ventricle and less blood being left after ventricular systole, which means more blood was pumped out. By the same token, if EDV increases, but end systolic volume also increases, this will result in a decrease in stroke volume. So yes, the amount of blood filling the ventricle has increased, but after systole, more blood or a great amount of blood is still left in the ventricle, which means very little was pumped out. Okay, so you should be able to understand these parameters. Anything that increases stroke volume will increase cardiac output. Anything that decreases stroke volume will decrease cardiac output. So how about an increase in ESV? An increase in EDV and a decrease in ESV affect cardiac output. We talked about that. That in that instance, stroke volume will increase, cardiac output will increase. If EDV increases and ESV also increases, would cardiac output increase or decrease? We just talked about that. Okay, so in that case, cardiac output will decrease because the stroke volume will also decrease.